All right, welcome to our review session for Quiz 13. Topics are externalities and public goods. And we're going to start with an externalities problem that comes out of the back of the chapter, the textbook chapter, one that we didn't go over in class, page 457, number 8. And this would be a good one for prep for the quiz tomorrow, obviously. So, planting a tree improves the environment. Assume that the value of this improvement to society is $10 for the expected lifetime of the tree. And this table gives the demand schedule for trees to be planted. So already, since we see it improves the environment, we're thinking about a positive externality, right? And the value of the improvement is $10. Should already start to be thinking, okay, so that means that the marginal social benefit is going to be greater than the demand curve in the amount of $10. Just kind of what you should be thinking as you first see the problem. So here's the table, and then the questions go like this. Assume the marginal cost for producing a tree for planting is constant at $20. Draw a diagram that shows the market equilibrium quantity and price for trees to be planted. So we're going to draw a graph here. This is for part A. Axes are quantity and price. And it gives us the marginal cost of producing a tree for planting, constant at $20. And then the market quantity, since it says the market quantity, we're just going with the market demand, which we have right here. We don't need to worry about the externality to find that. So basically, if we just graph this demand curve, that's one way to do it. Sketch that here, 0 and 30. It's 1 point. 6 and 25. 12 and 20. Should be right on that line there. 15 and 18. 10 and 24. 5 and 30. And 0 and 36. So what I've just created there with those dots is going to be our demand curve, which we could also call our marginal private benefit curve. And we can see that the equilibrium quantity there is where marginal cost or marginal private cost equals marginal private benefit or demand. And that is, you can tell there, at a quantity of 12 units, 12,000, since these are in thousands. So that's our market equilibrium quantity, 12,000 units at a price of $20. Next, what kind of externality is generated by planting a tree? We've already answered that when I first started talking through the problem. It's a positive externality. And then draw a diagram that shows the optimal number of trees planted and how this differs from the market outcome. I'm going to go ahead and just do this on the same graph, which is probably how I'd ask you to do it on a quiz. So to find the optimal number of trees planted, we need to find the marginal social benefit. And probably the better way of putting that is the price at which you would have it if you included that external benefit into the equation. In other words, if you have a quantity of 0 at a price of 30, if you include that additional $10 benefit, then that 30 goes to 40. And the 25 goes to 35. We just add 10 to each of these. Again, what we're saying is that, for instance, with a quantity of 6, while based on individual benefit, we might be willing to pay 25 to get 6,000 trees. We really should be willing to pay 35 to get 6,000 trees, because the social benefit is both the individual benefit of 25 to the individuals who are planting the trees, plus the social benefit of $10, adding up to 35. So we're going to draw this graph, sketch out 0 and 40, 6 at 35, 12 at 30, 18 at 25, 24 at 20, 30 at 15, and 36 at 10. There's our marginal social benefit curve, which is, just like we showed in this real rough sketch I did at first, $10 above the private demand curve. The marginal social benefit curve is $10, the amount of the externality above our marginal private benefit curve. And the intersection at marginal cost of $20 happens at a quantity of 24. So the optimal quantity, Q optimal, is equal to 24,000 trees. And it doesn't ask you for a different price. You usually don't have to worry about an optimal price, just an optimal quantity. So that's the optimal number of trees, is 24,000. And lastly, for part C, on your diagram, indicate the optimal Pigouvian tax or subsidy and explain how this moves the market to the optimal outcome. So again, whenever we have a Pigouvian tax or subsidy, it's just equal to the amount of the externality. So since it's a positive externality, we want it to be a subsidy. And if we subsidize consumers $10 per tree, then that will shift the demand curve up by $10, which we've already shown, so that the demand curve, the private demand, is kind of equalized with the marginal social benefit, which will then induce the market to create that 24 units. So it moves the market by shifting demand goes up, the subsidy increases demand. And if you do the subsidy in amount of $10, it increases demand by exactly $10 per unit, which gets you to the optimal quantity. So that's it. On the quiz, you will need to be able to deal with that's it for externality problems. You'll need to deal with the externality problems both with numbers and with just graphs, sometimes with no numbers at all, like you saw on some of the AP free response questions. All right, that's all I'll do with externalities. We've done a decent amount with that in class. I'm going to spend a little bit more time actually on public goods because we did less practice problems on those. Here's a couple of multiple choice questions on public goods to start us off with. Number 9 this is from the multiple choice problems that were on your Google Drive folder. Television programs are non-rival because, so one thing you need to be able to do for the quiz tomorrow is define and give examples of non-rival as well as non-excludable. So non-rival means that when one person uses it, it doesn't take away from somebody else using it. One person's use does not take away from another's. It can't necessarily be used up. And so out of our choices here, the supplier cannot prevent consumption by people who do not pay for it. No. More than one person can consume the unit of the good at the same time. That sounds right. Let's double check. Individuals ignore the effect their use has on the amount of the resource remaining for others. They might, but that's not what makes it non-rival. Whether or not the individuals ignore the effect is not really what being non-rival is all about. And then D, the market suffers from inefficiently low consumption. Now that wouldn't be the case because if you have a non-rival good, it may or may not be inefficiently low, maybe inefficiently high. So B is our answer. More than one person can consume the same unit of the good at the same time. That's really a restatement of this definition I wrote. And notice that choice A is basically a definition of this one, non-excludable. If the supplier cannot prevent consumption by people who did not pay for it, then it's also non-excludable. In other words, public television programs, since they're broadcast over publicly available frequencies, are basically non-rival and non-excludable. The supplier can't prevent consumption. Anybody who has a TV, they don't have to pay for an individual program. And they're non-rival, and that one person's use doesn't necessarily take away another's use. By the way, this is why, this is a little bit of ancient history. It's getting to be ancient history, but why public television, why publicly available broadcast stations are highly regulated by the government in a way that basically allows them to exist. Because before the technology of cable came along, which allowed television stations to charge people for viewing their station or for viewing individual programs, in today's technology, previously it was just they were broadcast over publicly available frequencies, and therefore they were basically both non-rival and non-excludable. To some extent you had to buy a TV, but it would have been hard for, if in a totally open public market, for individual broadcasters to make money without kind of government regulation of the market, licensing certain companies to use different frequencies to provide the programs that people watched. So it's a little bit of application there. Okay, number 15, consider an economy with just 2 citizens. If Jim's marginal benefit from mosquito control is $10, while Jane's marginal benefit is $25, then the optimal level of a public good like mosquito control occurs when the marginal cost of mosquito control is what? So 2 things we want to get out of this. One is that, remember that the marginal social benefit of a public good is equal to the sum of the individual marginal benefits from that good. Marginal social benefit is the sum of individual marginal benefits. So Jim gets $10 out of mosquito control, and Jane gets $25 out of mosquito control. That means that the public, society, these 2 citizens, Jim and Jane, are getting a total of $35 of marginal benefit, marginal social benefit, we should say, from mosquito control. Therefore, the optimal level of mosquito control, the optimal amount for society to spend on mosquito control, is where marginal social benefit is equal to marginal social cost. Marginal cost is equal to marginal social cost if you don't have a negative externality in play, which it doesn't mention here. So basically the answer is a simple $35, the sum of Jim's marginal benefit and Jane's marginal benefit. Pretty simple solution. It's one of those where you might look at and think, is it really that simple? And yes, it is. So one where you have to do that in the context of a table, the problem here is, again, from the end of the chapter in the textbook. Number 5, the following table shows Tanisha and Ari's individual marginal benefit of different amounts of street cleanings per month. Street cleaning would be a public good because it's both non-rival and non-excludable. Once you clean the street, you can't keep anybody from enjoying the benefits of the street cleaning, and my enjoyment of the street cleaning doesn't take away from your enjoyment of the street cleaning. Suppose the marginal cost of street cleanings is constant at $9 each. Here's our marginal cost. Here's our table, and A asks, if Tanisha had to pay for street cleaning on her own, how many street cleanings would there be? So Tanisha values the first unit of street cleaning at $10. And the cost of the first unit of street cleaning, the marginal cost, is $9. It's $9 for each street cleaning. So she would buy the first one because her benefit is greater than the cost. The second one, she gets $6 out of it. The cost is $9, so she wouldn't buy the second one. So the answer is 1. She would choose to buy 1 street cleaning per month if she were paying for it on her own. She would still get that benefit. She would get more than the cost. Then B asks, calculate the marginal social benefit of street cleaning and the optimal number of street cleanings. So we'd go, marginal social benefit is just the sum of the individual benefits. 10 plus 8, 18. 6 plus 4 is 10. 2 plus 1 is 3. So now we're looking at it as, for the optimal quantity, benefits greater than the cost for the first unit, benefits greater than the cost for the second unit, benefits not greater than the cost for the third unit. So the optimal number of street cleanings is 2. Society is going to get $10 of benefit out of the second street cleaning and only have to pay $9 for it. If we had to graph this, we would simply put price, quantity, marginal cost equal at $9. The individual benefits would look like this. Tanisha's would go like that. And Ari's starts lower, 8, 4, and 1. Ari's is lower all the way through. So if Ari had to pay for street cleanings on his own, by the way, he would buy 0 street cleanings. But then the social benefit, marginal social benefit, looks like this: 18, 10, and 3. So here's 2, here's 1. And there you go. This marginal social benefit curve is the vertical sum of Ari's and Tanisha's marginal benefits. And you may need to deal with that kind of graph too, so be prepared for that. Okay, hope this was helpful. See you tomorrow for the quiz, and good luck.